The Midwest Hydrogen Hub concept represents one of the most ambitious regional clean hydrogen efforts in the United States. With federal support, multi-state coordination, and plans that reference large-scale hydrogen production across industrial sectors, the hub is often discussed in terms of electrolyzer capacity, hydrogen volumes, and potential end-use demand. These figures are important, but they are not what ultimately determines whether hydrogen production can scale in practice. The determining factor is transmission capacity, specifically whether the electrical grid can deliver sufficient, reliable, and timely power to hydrogen production sites at the scale implied by nameplate assumptions. Hydrogen production at scale is fundamentally an electricity-intensive activity. Regardless of feedstock diversity or end-use variety, large portions of proposed hydrogen output depend on access to substantial quantities of power. In the Midwest Hydrogen Hub concept, this power is expected to come from a combination of existing generation assets and new clean energy sources, including wind and nuclear. However, the presence of generation resources within a region does not automatically translate into usable electricity at a specific site. Electricity must be transmitted, scheduled, and delivered through a grid system that has physical, regulatory, and operational limits. This distinction between installed capacity and delivered power is central to understanding hydrogen scalability. Nameplate megawatts describe what equipment could theoretically produce under ideal conditions. Transmission capacity describes what the system can actually supply continuously and reliably to a specific location. Hydrogen production depends on the latter. Electrolyzers do not operate on regional averages or annual energy potential. They operate on real-time delivered electricity. If transmission capacity is insufficient, delayed, or constrained, hydrogen output is limited regardless of how large the installed equipment base may be. In the Midwest, this issue is particularly relevant because the region spans multiple states, grid zones, and planning authorities. The hub concept crosses jurisdictions with different transmission priorities, congestion patterns, and upgrade timelines. While the region has significant energy resources, it also faces well-documented challenges related to interconnection queues, transmission congestion, and the time required to permit and build new lines. These challenges are not unique to hydrogen projects, but hydrogen projects are especially sensitive to them because of their scale and utilization requirements. Interconnection timelines are one of the first points where transmission capacity influences hydrogen feasibility. Large electrolysis facilities must secure grid interconnection approvals before construction and operation can proceed. Across the United States, interconnection queues have lengthened substantially over the past decade, with many projects facing multi-year delays between application and commercial operation. For hydrogen developers, these timelines directly affect project schedules, financing milestones, and offtake commitments. A hydrogen facility that cannot confirm when power will be available cannot reliably commit to production volumes or delivery dates. Beyond interconnection, ongoing transmission constraints affect operational performance. Even after a facility is connected, congestion on the grid can limit how much power is available during certain periods. For hydrogen production, this translates into lower utilization rates, variable output, and higher effective costs per kilogram. Electrolyzers are capital-intensive assets, and their economics depend heavily on sustained operation. Transmission-related interruptions or curtailments reduce output while fixed costs remain unchanged, placing upward pressure on hydrogen costs. The Midwest Hydrogen Hub concept highlights how these grid realities shape regional hydrogen strategies. While planning documents may reference aggregate production targets or installed capacity goals, the actual achievable output depends on how transmission capacity evolves over time. If transmission expansion lags behind hydrogen deployment plans, production will scale more slowly than projected. This is not a reflection of technological immaturity, but of infrastructure sequencing. Grid infrastructure has long development timelines, and hydrogen production must align with those timelines to achieve stable scale. Another dimension of transmission capacity is power quality and reliability. Hydrogen production facilities require not only sufficient power volume, but also consistent delivery to maintain operational stability. Variability in supply, whether due to congestion management or generation intermittency, introduces operational complexity. While flexible operation is possible, it comes with trade-offs in efficiency, maintenance, and economics. These trade-offs must be accounted for when evaluating how much hydrogen a hub can reliably produce over time. The emphasis on transmission capacity also reframes how success should be measured for hydrogen hubs. Rather than focusing primarily on announced megawatts or potential output, a more informative metric is delivered megawatt hours over time. This measure captures whether the grid can support sustained hydrogen production at the scale required for industrial use. It also aligns more closely with financial and operational realities, where lenders, off-takers, and operators prioritize dependable output over theoretical capacity. Importantly, this perspective does not imply that the Midwest Hydrogen Hub is unviable or flawed. Instead, it clarifies where attention must be focused to translate ambition into execution. Transmission planning, interconnection reform, and grid coordination become central components of hydrogen strategy, not secondary considerations. Without sufficient transmission capacity, hydrogen projects may proceed in phases, operate below nameplate expectations, or require interim solutions that affect cost and performance. This reality has implications for policy, investment, and project design. Policymakers supporting hydrogen hubs must consider how transmission development aligns with hydrogen timelines. Investors evaluating hub-related projects must assess grid access risk alongside technology and market risk. Developers must design facilities with realistic assumptions about power availability, rather than relying solely on regional generation statistics. The Midwest Hydrogen Hub serves as a useful case study because it brings these issues into focus at scale. By spanning multiple states and industrial sectors, it illustrates how hydrogen deployment intersects with existing grid constraints. It shows that hydrogen scale is not limited by electrolyzer technology alone, but by the infrastructure systems that supply and manage electricity. Transmission capacity, therefore, becomes the defining variable in determining how quickly and how reliably hydrogen production can grow. At this point in the discussion, Renee Energy points viewers to H2 Hub as a reference resource for examining hydrogen projects through a systems lens. H2 Hub focuses on how grid access, utilization risk, and infrastructure timelines affect hydrogen outcomes, providing a framework for evaluating projects beyond surface-level capacity metrics. For those working on hydrogen development or assessment, this perspective helps align expectations with operational reality. The Midwest Hydrogen Hub concept ultimately reinforces a broader lesson for the hydrogen economy. Scaling hydrogen production is not simply a matter of installing more equipment or announcing larger targets. It requires alignment between production assets and the transmission systems that supply them. As long as transmission capacity determines how much power can be delivered, it will also determine how much hydrogen can be produced. Recognizing this relationship is essential for translating hydrogen ambitions into durable, real-world outcomes.